So yeah, my name's Daz DeBoer or Daryl DeBoer. I work for Gradleware, and yeah, today we're just going to it's actually part of our based heavily on the training that we deliver that you can that Gradleware delivers. It's the just the native language part of the training. So we're going to do a bit of a workshop, go through some of the features that we've added in the last 12 months to support native languages in Gradle, and you guys will have plenty of chances to do some hands-on hacking on some little examples and stuff like that. I've never done this before. I've done this in a place where everyone's got an identical machine, and we've made sure they're all cloned with exactly the right thing. So, does anyone here not ever done C or native development on their machine that they're using now? Okay, good. So yeah, I mean the people with Macs will be fine because there's compilers. Oh no, you actually have to have the. No, you only need Clang. That's fine. That might not be. I don't know if you need developer tools. Anyway, we'll learn as we go. So yeah, I mean, I didn't. Apparently, there was some email I was supposed to send that would tell you all what you needed, and I didn't get around to that. So Rene's working on a VirtualBox image that we can use to hopefully, if we can't get things working, but what we'll do is we'll try without that, and what we might do is pair as well. So if you can't get an environment working, maybe go and find someone to sit next to, and you can work together on stuff. That's always fun, and you can learn from each other's mistakes. What I'll do is I'll hand out some USB sticks first. These have got the training material, so they've got the slides that we've got here, as well as they've got the labs that we're going to go and work through. So just copy the directory that's on there anywhere. So and then when we get we'll get going. Gradle. I don't think I put a Gradle distribution on there. Does everyone have Gradle installed on their laptops or machines here? Not quite. Okay. So we've got plenty of time. So if we can't get things working in the first lab, we might need to mix up and start doing some pairing and stuff. I think that's probably the safest option than trying to. If we end up, there's no point spending an hour and a half trying to get people's environment set up. If we can just sit down. I'm sure Gary here would love to have someone pair with. You can pair with a Gradleware employee down here. He's never seen this native stuff before either, so he's gonna learn it today with you guys. So yeah, so just a little bit of history. I guess firstly, has anyone? So I might get a bit of a feel. So who here has already used Gradle in production like at home at work? Who uses Gradle at work, just in any way? Okay, or at home on fun projects. Has anyone here actually used the new native stuff for building Gradle? Oh, yeah, you guys might learn something or might not. So, see, or you can teach me something. So and who here is actually actively working on some sort of building for native platforms, but actually hasn't used Gradle for it? Cool. So what are the tools you guys are using mostly? Make? Swig, okay. Anything else? Okay, Python, yeah. Anything else? Any other tools being used here? A-build. We've got the author of A-build here. It's another build tool, so trying to steal our ideas. No, I think it was the other way around actually. So yeah, cool. So yeah, so there's been some sort of C and C++ support in Gradle for a number of years. The early version of the first CPP and plugins were in 2011, so that's about when I started with Gradleware actually. They were, I wouldn't call them toy projects, but they were kind of more demonstrations of what could be done as opposed to things that were designed for use in the real world. So I don't think a lot of people were using them. We didn't hear a lot of feedback, so it was just let's see how we can make this work. So, but in the last 12 months or so, since the beginning of last year, we've put a pretty big investment into making the native support sort of world class. So and I'm pretty sure we've got to a point now where Gradle's pretty much ready to build to use in the prime time. We've got customers now who are using Gradle in real builds and building production binaries for multiple platforms in multiple environments. So it's pretty exciting. So the sort of things we've added in the last 18 months is we already had a bit of C support. We now have C, assembler, Objective-C, Objective-C++ support. Support for Windows resources. So if you want to include Windows resources in a DLL, that's been added. The ability to build binary variants. So that was one of the big limitations of the early plugin. It was basically worked the same as the Java plugin, produced a single output. And those of you who've worked in this space know that's almost never going to be satisfactory. So we added the ability to build debug or release build types, target different platforms, architectures, and operating systems, using different tool chains. So currently we support VisualC++, GCC, and Clang. GCC we support on Windows, Mac, and Linux. So GCC via Cygwin or MinGW on Windows. Visual Studio integrations, that was a big part of what we did, was basically being able to generate a Visual Studio project file from a Gradle project. So the sort of thing, if you guys are Java developers, you get used to, okay, I build my Gradle file, now I can just generate an Eclipse project or generate an IntelliJ project. So that sort of thing. We added Visual Studio support for something similar. And pretty basic CUnit support. So CUnit's a library similar to JUnit for C code. Other people have adapted that now for Google Test and a couple of other tools as well. So that's interesting. Stuff we haven't yet done is what we've done is we've done dependency resolution within a build. So if you're familiar with multi-project builds, I'll ask the question in a sec. So yeah, if you're familiar with multi-project builds, if you build a library in one project and consume it in another project, then Gradle's able to resolve those libraries just like in a Java app. What we haven't yet done is the concept of publishing these to a remote repository and resolving them from. So that's an unsolved space, and I think it's pretty much unsolved in the whole. There's no tool I'm aware of that does that well anyway at the moment. So there's no widely used tools that allow publishing to a remote repository and consuming, and we feel that's the future. That in the native space, that's where it needs to go. The native space is sort of lacking in this tooling, and we think we can help drive it forward. We want to support more tool chains. I think actually so there's basically better support for cross-compilation and better support for different compilers and different platforms compiling for more esoteric platforms that you guys might be using. And there's a bunch of stuff that, if you've heard any of the talks this week, on the last 2 days, about the new configuration model, that's something that's really critical to the native space that we're sort of planning, and it's all around performance improvements in the C++ space. So I'll explain later why it's more critical within the C++ space, but it's still in the planning stage, I guess. And finally, you need to be aware that support for this stuff is what we call incubating in Gradle. So, and incubating is a status of a feature where we say we're not guaranteeing backwards compatibility between releases of Gradle. So if we have something that's not incubating, it means that we're not going to change that. We're not going to break your build that uses it until we've deprecated it and given you a good chance to move on to something else, and then we'll remove it. With this stuff, because it's under active development, we want to be able to rename things. We want to be able to change things, and add stuff, and remove things that didn't work, remove experiments that didn't work. So we sort of, so right now, if you're using this stuff, you need to be aware that from one release of Gradle to the next, you might need to make some changes, and we always document them in the release notes, the things that you might need to change if you upgrade. I was going to ask actually. That's something. So I'm kind of assuming in this workshop that people have a basic understanding of how to use Gradle. I think because I can't actually like either you've done a workshop before or you've used Gradle a little bit, because we can't start from the very bottom and then also include the native stuff. There's a lot of differences in the native stuff, so if you haven't done it, you'll probably pick something up. But I'm going to be talking about tasks and plugins and things like that with the assumption that you understand those things. So I just wanted to be clear about that. Okay, so there's a bit of a paradigm shift moving into the native space from if you're a Java developer using Gradle and you have been using Gradle. And that, we're calling that sort of a model-driven configuration. So basically, if you think about how you define things, how you configure your build in Gradle now, you generally configure plugins and tasks. That's the things. You think of plugins, tasks, configurations, source sets. There's sort of, but a lot of the time when you want to add some behavior, you add a task. When you want to change the way something builds, you configure a task in a different way. And the approach we've taken in the native space is to step up a bit higher and say, actually, what we're going to do is try to build a model of what we're trying to build, as opposed to the tasks that are used to build that. So basically, in standard Gradle, a plugin will provide the tasks and the conventions and wire them up as well. Whereas in the new stuff, plugins provide some sort of capabilities, but they don't necessarily define the model that don't define the thing that you're trying to build. And most customization in the standard C++, in standard Gradle is just configuring tasks. In the native space, we spend a lot more time configuring the model, and the tasks are then built from the model. So you can see here we're saying that the model, plus some rules and plus some conventions, Gradle then takes those things and makes a task graph in order to execute. But the task graph is still the thing that we execute. So that's still all what happens at configuration time. And then when we actually execute, we still have tasks. We still have the same sort of model that's been run in the Gradle that you guys know and love. So sometimes you might think, this is brand new. This is nothing like what I'm familiar with. But I just need to emphasize that the task graph is still there. It's still accessible if you need it, and that stuff still works the way you're familiar with. So just a quick overview of some of the model elements that are involved in C++. So in the new native language support, a big one is source set. And if you've done any Java development, you know. If you've done any Java development, you know what a source set is. You know, it involves a bunch of sources grouped together that are used in a similar way. I'll grab that in a sec. It's all right. But a new thing we have is called a component. So a component is kind of an abstract model of something you're trying to build. Examples of components in the native space are executable, a native executable, so something you can actually execute, a native library, like a static library or a shared library, something that you can depend on. A test suite is another type of component. So because we have this rich model, we can say, okay, actually, here's a suite of tests. So you might have a unit test suite and an integration test suite. Those things are sort of components. A component can be built into a bunch of native binaries, and a binary is actually sort of an instantiation of that component. And the way in the Java space, we don't really differentiate those, because usually the component is my jar that I'm trying to build, my Java library, and the instantiation is a jar, and it's a one-to-one mapping. But in the native space, these things vary on a bunch of variant dimensions. So basically, you take a component and you instantiate it into a bunch of different native binaries, and the way they differ from each other, we refer to those as variant dimensions. So the native binaries are variants, and they vary in different dimensions. The key dimensions we'll talk about today are the linkage of a library. So basically, a library can be static or shared. That's how it's linked together. The build type of a library, such as a debug or a release variant, and the platform that it's built for. There's another one that we talk about, another variant dimension we talk about is flavor. So tool chain, I think that's, if that doesn't sound familiar to you, a tool chain we consider to be a set of tools that works together to produce a binary. So the Java compiler and the various tools that come with it would be considered a Java tool chain. GCC is a set of tools which involves a C compiler, a C++ compiler, an assembler, and a linker, and a few other things. That's a tool chain. Clang is a tool chain. VisualCpp is a tool chain, as far as we're concerned in Gradle. And then we have a lot of domain object containers. This is something that is just a standard Gradle, but we use them quite heavily in the native space. So we have, say, a container for all the executables within a build, or we have a container for all the libraries within a build. And that's the way we sort of define model elements, is often by adding them to a container that Gradle provides. So Gradle provides a container, an empty container, and you say, okay, I want to add an executable to that, I want to add a library to that container. That's how you define these things. So feel free to jump in with questions at any time. I don't want to get ahead of everyone, and I don't want to rush through this material. So just anyone have any questions, just let me know. Okay, so we have a bunch of plugins that provide the native support in Gradle. The usual mechanism there. So usually what we're doing when we're adding native support to our build is we're applying the plugins. What do the plugins do? They're basically providing the core model elements, so these component types, executable, native library, test suite, all those sort of, they can provide those types. They provide the support for languages like C or C++, assembler, so you might have different plugins that add different sort of language support. And they all add support for the standard tool chain, so the tool chains I referred to earlier. So in this case, I think it's pretty clear what this is doing. We're adding support for 4 different languages. We consider Windows resources a language, it kind of is. And so we're adding support for C, C++, or sorry, C++, C, assembler, and Windows resources. And each of these automatically includes the core model, this core model support, as well as the standard toolchain support. So that's the way we've segregated at the moment on the language level. This possibly is going to change a little bit in the future. We might start saying, let's actually split out the model support from the language support and actually say, I just apply 2 plugins. Apply one that says I want to build native components, and another one that says I want to build it with this particular language. I'm not quite sure how that's going to look, but this is how it looks now, and it will stay this way for a while anyway. Okay, so tool chains, as I said before, a tool chain is kind of just a set of tools that works together. And in your Gradle build, you get a set of default tool chains out of the box. If you don't know what tool chains you want to work with, then Gradle just says, we're just going to see what's available and we'll try to use the best one for you. So the idea is to make it work as easily as possible out of the box. So we currently, I said, support Clang, VCC, and Visual Studio, Visual C++. Yeah, so basically what Gradle's going to do it just iterates through the list and finds the first one that can be used. And so a lot of the time it's really nice to get something working in the first place. You just fire up your Gradle build, don't add any toolchain configuration, and it should, if you've got a toolchain that Gradle can understand, it will work. That's why I was asking you guys if you've got any, if you've done any development on your machines already, because if you have, you've got a toolchain. You already have this. If you don't have, then that means we need to get something set up to start with. So yeah, that's if you have the defaults, but you can explicitly say which tool chains you want to use in your build script. So that's part of configuring the model for your build. So it's I'd say what usually happens in the development process is you'll start off playing around and you won't have defined any tool chains. But then, in a real world build where you really where you want to lock down, you want to control what's going on, that's when you're going to define, I use these 3 tool chains, and you might have some custom tool chains that you need for your build to build for a particular platform, which we'll get to a bit later on. And finally, yeah, Gradle's not going to just use the first tool chain and assume it's going to work. If you're building for Windows, Gradle's going to go ask the tool chain, can you build for Windows? No? Okay, I'll try the next one. And basically, you can imagine it's a list of things and it tries to find the first one. Given a particular target platform, it uses the first available toolchain that will build for that platform.
So that means you can cross-compile with Gradle?
You can cross-compile, yes.
Okay.
Yeah, I'll get to that just in one sec. So this is the set of default tool chains. So effectively, if you don't do anything, don't define any tool chains, this is the exact configuration you get. You get Visual C++ tool chain being the first one. You get a GCC tool chain as second priority and a Clang tool chain as the third priority. So the question was, is it possible to cross-compile with Gradle? And so cross-compile means usually means you're using GCC, but you want to build for a platform other than the current platform. That's kind of what you mean. Yeah. So you can both define a platform that's not that So cross compilation in some ways is simple. You say, okay, I just want to build for 32-bit. I'm running on 64-bit. If GCC can do that, it says yes, I can, and it'll do that. If you say I want to build for Solaris and you're running on a Linux machine, that's a more complex thing. Usually you've had to build a special version of GCC to do that. So in that case, what you do is you actually configure a toolchain directly. I can't remember if we have a slider for it, but you basically say, there's a target keyword that you can use to configure the toolchain. You say, I target Solaris, and here's the executable I need to use, and things like that. So you can configure the toolchain specifically and say, and that toolchain then becomes one that's able to build for Solaris. I think there is a slide here somewhere, so we'll see. Okay, so the Visual C++ toolchain, the first one in the list, basically detects your Visual Studio install on your machine. It checks the Windows registry, looks for all the various tools that are involved in that toolchain. It looks for the Windows SDK that should be in certain locations. It depends what version of Windows you're running. So there's quite a lot of sophisticated logic in there that's trying to find the install of Visual C++. It will use the newest one it finds, so the registry tells us usually this is the current version of Visual C++ to use, and we try to use that. Yeah, we support 2010, 2013. I think someone had it working on 2008 as well, but we don't have test coverage for it, so it's kind of hard for us to say we support it when we don't have that test coverage. And what you can do with Visual C++ is you can target Windows, obviously. I don't think you can build for any other operating system, but you can target 32-bit Intel, 64-bit Intel, 64-bit Itanium, and ARM on Windows. Windows running on those different architectures. And so here's just a way, so if you decide, oh, I actually want to, Gradle can't find my default Visual Studio install, and I need to tell Gradle where it is, or I want to add a new one that's not on the path, you can configure some details about a Visual C++ toolchain by giving it the installation directory and the Windows SDK directory. So that means that this is going to be used in this particular Visual Studio install, this particular Windows SDK, not one that it found in the registry. So who here has done Visual Studio or Visual C++ development before? Okay. So one thing that you usually have to do when you're using Visual C++ is you need to open a special console that's actually configured for a particular environment, and I think it sets up a bunch of paths and a bunch of things like that. It adds a bunch of stuff to the path. So with Gradle, you don't need to do that. You don't need to run Gradle inside a special Visual Studio console in order for it to work. What we've done is we've gone and looked at what those scripts do and tried our very best to replicate that. So we actually set up the environment so that Visual Studio will work. So that means you can now run Visual Studio on your CI server much more easily, and you can run Visual Studio from Cygwin if that's your preferred shell. You don't have to be running inside a special Visual Studio command prompt, which is sort of the way that people usually do that. That's kind of a nifty thing because I think it frees people up to do things that they can't normally do. So then we have the GCC tool chain. GCC, has anyone here used GCC before to build C stuff? Yeah, most people. Okay, cool. Clang and GCC I don't even know if we have a slide for Clang. Let's see. Oh, we do. Good. Okay. Clang and GCC are virtually identical in a lot of ways. So basically, it looks in the path for an executable called GCC, and for one called G++, and the linker called. We use GCC to do the linking as well. And those names are configurable. So if you have a cross compiler that you say, actually, no, my GCC is not called GCC on my platform, it's called GCC-3.2, then you can say that's the one I want to use. And you can configure 2 different GCC versions that way with different names. You can also give it the path to say, actually, this is a GCC that's found in user local GCC3 bin. Obviously, the problem with this sort of approach is it does tie your build script to a particular, say, release of Linux or something that has GCC in that particular spot. But we haven't found a really, what we'd like to move towards is something more like I want a GCC 3 version, and Gradle will look for all the possible GCCs and find one that's version 3. We haven't quite got there yet. So yeah, GCC, I think I mentioned before, it supports both Cygwin and MinGW on Windows. So MinGW is minimal GNU for Windows. It's just a port of GCC to, and a bunch of other GNU tools to Windows. Allows you to run just command line, build command line apps, build from the command line in Windows without having Visual Studio installed. Targets, so by default, it'll target the x86 processor and the AMD 64, so Intel 32 and Intel 64 architectures on whatever operating system you're running on at the time. So whatever the default operating system for that install of GCC is. And you can target additional platforms for cross-compilation using a DSL, which may be on the next slide, or it may be something we'd have to talk about later. Let's have a look. Oh, no, it's not the next slide, we'll see. So Clang toolchain, basically, if you know how to use the GCC toolchain, you know how to use the Clang toolchain. They're implemented in almost an identical way in Gradle. So the configuration's the same, the executables are named the same, but they're just the default values. We're looking for Clang and Clang++. One thing to be aware of if you're using a Mac is that the GCC that is available by default on Mac is actually, I think it's just a symlink to Clang pretty much, and it actually doesn't behave like GCC in some ways. So we don't use that as GCC. We say, well, that's not really GCC, so we're not going to use it. We're going to wait, and we'll use it as we'll call that Clang and use it as Clang. You can install GCC separately on I think using Mac ports on the Mac, and then you'd have both. So, any questions about tool chains before I go on there? So one of the things is we're not going to spend a lot of time configuring and using tool chains here, because I'm just hopeful that everyone will have a tool chain that they can build something with, and to try to get multiple tool chains working and try to get everyone with Visual Studio might be a nightmare. So, do you have a question there?
Yeah. Is it possible yet to create a custom tool chain for something that's, like, for example, targeting EXWorks, where you compile into libraries, but they're not really shared libraries and they're not really executables, but like the commands to create them are essentially the same? I mean, have anybody thought about that problem yet? Or?
So the question is, can we support sort of tools that look a bit like a tool chain but aren't really a supported tool chain?
They're a real tool chain, but the kinds of things that they create aren't exactly the same.
Right. Yeah, I wouldn't be surprised if you could actually do that. I wouldn't say that. I don't think anyone's tried. So, I mean, effectively what we can do is we can configure, for a tool chain, we can configure the path it's found, the tools are found on. We can configure the executable to call to compile each language, and the executable to call to link the various object files into an output file, and any extra arguments you want to provide on the command line. So if you could do that, you'd end up with a .so file that wouldn't be really a .so file, I guess is what, yeah. So it won't work beautifully, I don't think, but it might be possible to if you know what you're doing, you might be able to get that. You may be better off just using the underlying compile tasks directly or something, but yeah. There was talk, there was some people talking to us about wanting to map this. Oh, we actually just want to use make under the covers, and we want to use Gradle to wrap this all. I said, well, you might be able to build a make toolchain, and actually just have the toolchain implementation call through to make. I didn't recommend that, but I said, there might be ways to do this, or a remote. I want to build on a remote machine. Well, you might be able to have a toolchain that actually doesn't do things locally; it does things remotely. So it's an abstraction that we might be able to use for all sorts of things. So far, we've kept it pretty simple, and we haven't used them in that way. But who knows what people will come up with? It's out there. Any other questions before we move on? Cool. So the first software component I want to talk about is the executable, a native executable. So it's the simplest thing. Effectively, it's a native binary component that you can run, you can execute, right? So I think if we want to build a Hello World app in C++, we're going to be building an executable. Within a project, an executable is a domain model element, and it needs to have a unique name. So what we do is we add a named thing to the set of executables, and that basically tells Gradle what to build. So basically, here's how we're going to define an executable. We're going to say this is executables container. That's defined by Gradle, and here we're just adding something to it. We're basically saying I want my application to be in the executables container. As soon as you do this, Gradle goes, cool, I know what this build does. This build builds a native executable. Cool, I know it. So then what Gradle from there can work out things like, oh, I want to build, let's see if there's a tool chain that can build the binaries for this executable. Let's see if there's build types defined, let's define all those things. But without this amount of configuration, Gradle will just assume you're not trying to do anything. So for each executable, the component, Gradle defines a number of executable binaries, variants, whatever we want to call them, and tries to build one or more of those. To build one of those things, Gradle defines a bunch of tasks. So this is where we get into the Gradle that we're all more familiar with. We've got this model that sort of abstracts away the task, but then now we've got to actually build this thing. We need to build a task graph to build it. So you imagine what we normally do. We're going to build a bunch of compile tasks, once for each type of language. So if we've got C language sources, we want to compile those. If we have multiple source sets, we compile them separately. So you can say this source set can be compiled in isolation from this one with different header files. If we have C++ sources, they get compiled. If we have assembler sources, they get assembled into object files. We end up with a bunch of object files after that. Then we have a link task that actually links all those object files into a single binary. And we have this, what we call a lifecycle task, and this effectively is the name of the thing we're trying to build. It's the entry point if you're trying to build that variant, you basically call that task. Gradle adds one more task to the set, which is an install task. So for an executable that has no dependencies, that's just a really self-contained thing, it's not really necessary. You can just execute something directly. But if you have an executable that relies on shared libraries, then those shared libraries need to be in the right spot to be able to execute that. So what Gradle does, it has like a developer install. It builds a developer image of these things. And this name is not install into production or anything like that. It's more install locally so that I can use this thing, so I can try it out. So today when we're doing the labs, we're going to be doing install my executable so that we can actually then run my executable and see what it does. So all of these tasks are incremental. Does that mean something to people here? It means that, so incremental means that if the outputs are up to date with respect to the inputs for each of these tasks, we just don't do anything. We say they're up to date, and you'll get that lovely little up to date printed out next to there. We also have incremental compilation in here, which means that even if the sources have changed, but changed in a way that doesn't change the outputs, then they're considered up to date. Or even if a header file's changed, but it actually has no impact on this set of sources, then that compile task ends up to date as well. Yep.
Is there a top-level task that has all the installs as dependencies?
No. Recently added, there's a top-level task that the assemble task will build all the things, but it doesn't install them all. But it's very easy, and I think we do a lab where we're going to show how to really simply create your own install everything task. It's effectively tasks with type install executable. It's a task that depends on all tasks with type install executable. Sorry, the question was, is there a top-level task that does all the installs? And there's not yet. So that's all kind of not very interesting if all we're doing is compiling, but the next thing what Gradle lets you do is it lets you define how you want to compile your sources. So this is where things get a little bit more interesting. So for every executable binary, so every variant that we're trying to build for a particular native executable component, we can say, use these compiler arguments for this source for these sources, use these compiler arguments for C sources, use these linker arguments. So you can basically define, and the way we define them is we define them in a rule. So here what we've got is here's my executables container that I showed before. That's what Gradle's defined. Here's the application I'm defining. So I'm saying I'm building a component called my application. Basically saying for every binary, so for every executable binary variant, configure the compiler and the linker in this way. So configure the C++ compiler with this macro defined. And that's a macro with no value. Consider the C++ compiler should also have macro2 defined with a value. So it's like -d macro2 equals value. And add a bunch of random compiler arguments. So we've added a -g that adds debug symbols to the output on GCC and a no excess control, just some other random argument that we decided to put in there. So that's good. That's how the C++ sources are going to be compiled. And then we have how the link is going to be called. The link is going to be called with -s. So this is we can do this for all binaries. There's also ways to say I only want to do this for particular binaries, and we'll get to that later. That allows you to customize certain binaries in certain ways. So someone already asked a question about how they configure the source sets if they're not in a conventional location. The fact is, I say conventional location. I don't believe this is a convention. I don't think it's probably almost, the chances of Gradle knowing how your source files are already configured is infinitesimally small, because I don't think, get this feeling that everyone does something different in the world. So you're going to have to configure where your sources are. So I'll just go through what source sets are in the native space first. So we have the concept of a language source set. So a language source set is a source set of files for the same language. So a set of C++ files, or a set of C files, a set of assembler files. They also may, for certain languages, have a set of header files associated with them. So you can have C++ plus the header files associated with that C++. And we call that it's a language source set. So that's a key concept here. Language source sets are grouped together into a functional source set. So a functional source set is a type that actually says, I've got, it's for example, all the sources for a particular component would be a functional source set. So if you have C and C++ and assembler sources going into one component, those three language source sets are a part of the same functional source set for the component. And you can add extra language source sets. You can associate extra language source sets directly with a component, with an executable or a library, or you can associate extra language source sets with a functional source set, which can then be shared amongst different components. So it's quite a flexible model there. But generally what we're going to be doing today is a component, so an executable or a library, will have a single functional source set, and then we'll have one or more language source sets in that functional source set. So by the conventions that we use in Gradle is, so at the high level we have, for a component, we have a functional source set. That functional source set name is the same as the component name. And then within that functional source set, we have a language source set per supported language. So if you've applied the C and the C++ plugins, you then have a C and C++ functional source set C and C++ language source set within the functional source set. So this is the definition of what the conventions are for every component. There's a functional source set, and it's named sources dot the component name. So sources hello for an executable hello. And then for every language, there's a sources.hello.language. So in this case, this implies that we've applied three plugins, the C++, the C, and the assembler plugin to get those source sets. This is the model of these source sets. So this is saying how they're programmatically represented, but it also represents the convention for where the sources will be located on disk. So we assume that there's going to be an src directory following the sort of that Maven Gradle convention. Then there's a Java, that's like main, and then we have Java, Groovy, Scala. We have the equivalent here, src, hello, CPP, C, and ASM. So if you look at the lab we just did, there was a source directory, src, there was a hello directory, and there was a CPP directory, and under that there was a, whatever that file is called, .cpp. So I said before that you can add additional language source sets to a functional source set. So here we've got the conventional functional source set for my component. It's called hello. But what I'm doing is I'm adding a bunch of extra source sets. I'm saying not only is there the base CPP source set, I've got a bunch of extra CPP files. Why do we have this? Maybe we want to compile those C++ files differently with different flags than the other ones. Maybe we want to include them only in certain binaries and not in other binaries. So like, let's say they're Windows-specific sources and we only want to include them in Windows. There might be all sorts of reasons you want to configure those things separately. So here we've added a C++, a C, and an assembler source set to our.
Is that argument, is that type?
This, yeah, so this is actually a pattern that's used for what we have. We've got a domain object container in Gradle. So this is a domain object container, executables, and we're adding a thing called hello. This is a polymorphic domain object container. And what that means is you can add things by name and you need to give them a type to create them. So we use this a lot. We use this in the new publication model, and we use this in other parts of Gradle where you're saying, okay, I want to add something with a particular type. Once you've added it, you can reference it without the type, but in order to create it, you need to provide the type. I already mentioned this, but the source locations follow that conventional source, follow the naming of the actual source set model quite closely. So basically, for that single executable named hello, this would be where your conventional sources would be stored. You'd have a hello directory, a CPP, and then a bunch of C++ sources, and then a headers directory and a bunch of headers in there. And you can configure this, but this is what you'll get if you don't configure it at all. So in a lot of the labs we do today, to avoid having to configure it, we put these sources into conventional locations. So yeah, again, just jump in with any questions about this stuff. So the next lab, what we're going to do is we're going to look at non-conventional location of sources. So what if I have my own convention and I want to define where the sources live? There's a pretty simple DSL for defining that. So here we've got a component called myapp. So we have a functional source set called myapp. And we're saying, actually, my C++ sources aren't where they normally are. They're not in src, myapp, CPP. So what I'm saying is the source for my C++ language sources, the source files are located in two directories, in code/app and code/util. And we want to include every star.c++ found in those directories. So I mean, you might use CPP or you might use capital C for however you like, so you can define your own includes for what sources are included. And then to define the headers for a particular component, you say, here, in the same way you can configure the source directories that make up the headers, and also you can configure the includes for headers.
So with the native stuff, do you have to always use closure type systems, or do we do source, myapp, CPP, sources, source, all the dots?
You can, yeah, you can do either. Yeah. So this, I mean, we usually do it this way. It sort of looks more like a DSL, but there's no reason you couldn't do source.source dirs. And in fact, some of the slides I do that because it fits on the page better. So this is the equivalent of saying source.source dirs equals.
So basically everything we do like when we work in Java.
It's the same. It's the same. Yeah. The actual underlying infrastructure that applies the DSL is identical. So there's nothing new. So that polymorphic domain object container, that's not a native specific thing. That's actually a general purpose Gradle piece of Gradle infrastructure. That's why it's in the publication plugin as well as in the native plugin. And I think it's probably filtering into a few of the other plugins as well. So, yep.
Can I add headers that I don't want to export?
Sorry, what's that?
Can I add headers that I don't want to export, like package export?
Yeah. So this is something we want to model. Sorry. The question is, can you add headers that you don't want to export, as well as so private headers and public? This is something we want to model better. So right now, you either have headers that are exported here, or you have headers that are implicit, which you include, that are found implicitly with the sources, which is not great, right? It's not the right way. What we want to do is model private headers and public headers, possibly exported and public as well, shared as well as exported. Like there's a bunch of different things, and we've got a story to do that pretty soon, is to actually model our source sets better. I think Rene was supposed to be working on that and he got pulled off onto something else. So, yeah. So that's, because right now it is fairly simplistic the way we model our headers. So, yeah. This means these headers are going to be both available when I'm compiling this as well as when something's compiling against me, which is not always the same. You don't necessarily want that to be the same. We're going to run out of time for sure. So libraries is the next thing we should talk about. So we've talked about executables, but it'd be a pretty boring world if all we had was just executables and nothing else. So we build libraries so we can share code between executables and different applications and things like that. Very similar concept to executables, so this is pretty straightforward. You add something into the libraries container to define a library, and it has a unique name within the project. Same as an executable, you can give it our compiler and linker arguments. We can, given any library component, so for an executable, Gradle just built a single executable binary by default. For a library, Gradle straight away has two different variants it can build. It can build a shared library binary for this library, and it can build a static library binary. So is everyone familiar with shared and static libraries? Is that something I don't have to explain? Cool. Okay. So then when you use an executable, you can say, I'm depending on a particular library, like I'm going to use that library. I can either use the static or the shared version of that library. Shared version, shared in Windows is a DLL, and shared on Unix is .so. So we saw before the binaries.all block, which we said just configure every single binary in this project. We also have this sort of by type-based rule. So we basically want to say, we want to configure every executable binary within this project, or we want to configure every shared library binary within this project, or every static library binary. So basically lets us target compiler arguments or any other sort of configuration against binaries of a particular type. So so effectively what's going to happen is this piece of configuration will be applied not against every binary, but against every binary that matches that, that sort of filter, that type filter. We touched on this a little bit earlier, but we can configure binaries by the scope. We can configure binaries by their scope, or that we can add rules that are scoped to a particular component. So in this case here, we've said, here's some rules that apply to every single binary that we're going to create in this project. Here's some rules that apply to every single binary created for the main executable, and likewise for here's some configuration for every binary created for the hello library. So so when you think about it, we can have rules that apply that configure every single binary, rules that configure every single binary of a particular type, which we saw on the last slide, and then rules that configure every particular binary of a particular component. And you can even do every particular binary of a particular type for a component. We have that flexibility as well. And so this sort of these bits of configuration are CPP compiler.define, CPP compiler.arg, linker.args, things like that. So, yep.
You also have methods for filtering specific binaries based on certain rules.
So the question is, do we have any methods? This is a regular domain object collection, so it has the .matching method on it. So you can use that to say, look at all the binaries and filter out certain ones and only apply. So yeah, these are domain object collections. So you can use any of that, the regular stuff that you can get there. With type is just one of those methods on there. So I don't think I have any examples of using .matching today, but yeah, it's a way of saying I want to target for when we get to doing build types and things like that, it's a way of targeting all the compiler arguments for a particular build type. It's one way to do it anyway. So libraries on their own are pretty boring, just like executables are, but when you bring them together, they're very exciting. So what we're calling it here is a library requirement. In the Java space, it's a dependency. It's a jar dependency or a module dependency. Basically saying, and we often model in the native space, we often model dependencies at the level of the source set. So we say this source set depends on that library. What that means is the sources in here need the headers from that library in order to compile, and things that are built from these sources need the stubs of that library in order to link, and they need the actual dynamic library at runtime. So the functionality in here will require the dynamic library at runtime. So, and when you declare this library dependency, we can also specify a linkage that we want. So I mentioned before, when you build an executable, you can say, I want to link against I want to use the shared library of this, I want to use the shared version of this library, or I want to use the static version of this library. Basically, we call that the linkage. So we're saying, I'm using library B with the static linkage. Effectively, I'm an executable, I want the library B with the static linkage. And we also have an API linkage, which allows you to do things like template libraries that don't actually have a runtime or a link time representation. So they're just a bunch of headers. So how do we actually do this? There's two syntaxes you can use for declaring a library dependency. So from a source set. So we're saying, so here we've got, this is our source set. You asked before if we can use the dot notation instead of the squiggly brackets, and that's exactly what we're doing here for sort of conciseness. But we're saying the main C++ source set has requires a bunch of libraries. It's requiring a library named lib1. This is a library within the same project named lib1. This is a library in the same project named lib2 with a static linkage, and a library named lib3 with a shared linkage. So the default is going to be shared. So by default, Gradle's going to choose the shared linkage to use. This is kind of the preferred notation because it's sort of a dependency notation, and we want to start doing some clever things in the future with it. You can also just reference the instance of the library that you've got in a container. So here we're just saying, I depend on, give me the libraries container in this project and get me the thing out by name. So this line, the first two lines here are exactly the same as the first two lines up here. But this is actually a preferred syntax. Yeah, the default linkage is shared. So think of this as the same as declaring a dependency in your Java project. So finally, with a multi-project build, we have project dependencies. So we can basically say, I'm not just depending on a library like that's within the same project. I'm depending on a library that's built in another project. So here we've got two projects within a single multi-project build, and we're saying my app CPP sources have a requirement on the library, the hello library from the hello project. And in this case, my hello C++ sources have a dependency on the util library in the util project, and they want to use that as a static library, not as a shared library. Yeah, or the binary. Yeah. So there is another way to declare dependencies on a library by saying my component. You can't currently say my component depends on a library, but you can say a particular binary for that component depends on a library. Effectively, that just means every source set that goes to make up this binary will get this library of dependencies. So in this case, we're saying every binary in my project depends on the library, the hello library. And yeah, basically every language source set is just going to grab that, is going to have that requirement. Another way we can declare dependencies is between source sets. So rather than from a source set to a library, which is a component and can be built separately, we can just say my main C sources depend on my IDL C sources. And this helps us, if we had some specific Windows sources, they might just depend on some common sources. So we can structure our source sets like that without having to say this is a separate library. We can just have sets of sources that depend on each other.